Hello there, and welcome to my EP2E04 design project presentation. This project's goal was to design and build a finite state machine that cycles through my student number. The number is what you see currently displayed on the screen. So let's run through the process. The first step is to decide what the outputs need to be for each digit. We have a total of 6 outputs, 4 being used to represent the digit, and 2 being used as counter bits to keep track of repeating digits. For most digits, we don't care about the status of the counter bits, and so I started by assigning all of the don't care conditions to a 0 or low. The goal is to minimize the amount of logic gates needed, and so by setting most of the conditions to low, I am limiting the possibility for a flip-flop to output a high 2 times in a row. If a flip-flop never goes from a high to a high, then at least one of its inputs will always be 0. Next, I generated my input table, and then started a K-mapping procedure to determine my logic equations. Using only the sum of products, I got all my logic equations and built a simulated version of my circuit. However, this was highly unoptimized, and I knew it could be simplified. So, I went back to the design stage. I implemented products of sums where I could, and made a small adjustment to my original counterbit setup. More details on those optimizations can be found in the report. After running through the K-mapping process once again, I generated smaller logic equations and a much simpler circuit. This circuit uses a total of 7 gates, as opposed to the original which used 13 gates. In total we have 6 flip-flops, 6 AND gates, and 1 OR gate, making for a total of 6 chips. As you can see here, the flip-flop outputs are then connected to the decoder chip, which is then wired to the 7-segment display. The blanking pin on the decoder chip is also connected to the clock, which means that the display will turn off in between numbers. This should make it easier to ensure that successive digits are getting repeated the correct number of times. We now test the circuit's outputs. The first thing I'm going to do is set my don't clear pins to low, to have my circuit start with the first number in my student number, which is 4. As soon as I flip it to high, we should see the 7-segment display cycle through the student number. As we can see, it cycles through the student number perfectly, which means we are ready to start building our physical circuit. So here's what the finalized circuit looks like. We have our flip-flops on the bottom and our logic gates up top. We have our Q1 flip-flop, our Q2, Q3, Q4, counter bit number 1, and counter bit number 2. Then on the top we have our logic gates, where we have our AND gates, our OR gate, and our final 2 AND gates. Then the flip-flop outputs are connected to the decoder chip, which is connected via the resistors to the 7-segment display. And then the last thing to notice is in the bottom left of the screen, the black wire is going to help us toggle on and off our clear and preset pins to help us get into our starting state of the digit number 4. So let's begin. We connect power to our circuit, then connect our clock, then we set our clear pins to low to get into our starting state at 4, and then as soon as we flip it to high, it should start looping through our student number. And as you can see here, we loop through the student number perfectly. This design project was a great way to show off the skills I've learned in this course, and I'm happy that it worked just as designed without any hiccups. I hope you enjoyed my presentation, and thank you for your time.